Meltdown. That's what we're going to be talking about tonight. First of all, though, who am I? Hi, my name's Henry. For those who don't know me, that's my dog, Carson. I didn't put a picture of me because you can see what I look like. I'm a fourth-year CPE student. I enjoy rock climbing and basically rock climbing, hiking, basically anything where you get to go outdoors. Also really like sailing, but I don't get to do that very often. And yeah, all right, let's move on to what is Meltdown. So here is a large block of text. That's what describes what Meltdown is. Meltdown Inspector, we're not going to talk about Inspector today because it's even more complicated than Meltdown. Exploit critical vulnerabilities in modern processors. These hardware vulnerabilities allow programs to steal data which is currently processed on the computer. While programs are typically not permitted to read data from other programs, a malicious program can exploit Meltdown and Spectre to get hold of secrets stored in the memory of other running programs. It might include your password stored in a messenger, a password manager or browser, your personal photos, emails, instant messages, and even business critical documents. That was a lot. So quick translation. Basically, Meltdown is a bug in the physical hardware of your CPU. It's not a software bug, it's a hardware bug, which has some really interesting consequences. That means that one process running on your computer can see what other processes running on your computer are doing, which violates like the #1 rule of operating systems. So we're going to talk about how that works today, why that's really bad, and yeah. Oh, and by the way, if you have questions throughout any of this, we're going to be going over like a lot of pretty advanced topics, particularly if you haven't taken OS or a computer architecture class. So if you have questions, if you feel like they're dumb questions, please raise your hand and ask. I'm trying to make this as entry level as I can, but it's still like a lot of material if you haven't been exposed to these concepts before. So anyway, carrying on. How does it work? Another quote from the original Meltdown article, I think it's from the abstract. Meltdown exploits the side effects of out-of-order execution on modern processors and reads arbitrary kernel memory locations including personal data and passwords. That's a lot of text. Again, with a lot of big words like out-of-order processors and kernel memory. So pretty much the entirety of this talk is going to be breaking down this sentence and explaining what this actually means. If you try to understand the sentence, though, you basically understand how Meltdown works already. So, yeah. So these are sort of the things we're going to be going over today. Prerequisite knowledge in order to understand Meltdown. We're not actually going to talk about timers, but timers are like really simple. So I don't have a slide for them. But we're going to go over virtual memory, out-of-order processing, caching, and kernel space versus user space. Starting with virtual memory. Okay, so imagine that you are in like the 1970s or something. I don't know exactly. Operating systems are hot on the scene. Every program you've run up until then has a block of memory. This is all the memory on the machine. Let's say your program wants to access address X8000. Sorry, my handwriting is abysmal. It can just do that because it's the only program running on the machine. Nothing else wants address hex 8000. Assuming the machine has that much memory, that just works. But then now we want to run multiple programs. That's like the entire job of operating systems, is to allow us to run multiple programs on the same machine. So now we have, this is program 1, and now we're going to have program 2. And program 2 also wants to access address hex 8000. Now we have a huge problem, because unless we specifically say so in an operating system, two programs shouldn't be able to talk to each other. They shouldn't be able to see what the other's doing, and they shouldn't be able to affect one another, unless we explicitly say so. So the fact that they can read and write the same memory location is a big problem. And all programs, all modern day programs, still basically act like they have the entire machine to themselves, and they have all the memory that their hearts could desire. So, how do we fix this? We implement virtual memory. So instead of having each program just accessing address hex 8000, I'm just going to abbreviate it to P1 and P2. Each of them go through what we call a page table. And they have separate page tables. Each page table does a translation now we're going to be working in virtual addresses over here. So they still both think they have access to hex 8000. But now the page table is going to translate it. So let's say this page table translates into hex 2000. And this one translates it to page hex 4000. So virtual memory is basically just a mapping of virtual addresses that the programs are using to physical addresses, which is the physical location of that data in memory. You can see on this cool little diagram here, basically kind of same thing I drew. We've got our page frames. The physical memory locations are called page frames. They're 4K each, which then goes through a memory map into our physical, sorry, got that the wrong way around. This is our virtual memory. So it's divided up, I didn't draw this on here, they're divided up into 4K pages, which is basically our units. They're divided into 4K pages, which go through the memory map, which map to physical memory page frames. And we're not talking about disk storage. That's a talk for another day. This allows multiple processes to access the same virtual address, but they actually be talking about different physical addresses. And there's some other cool stuff in virtual memory, namely these permission bits. So basically each page table can say, hey, this process, it has read access to this memory, but not write access. It can't write to it, it can only read from it, or it can only execute it. The three main bits, there are a lot of others, but the ones we care about mostly are RWX, read, write, and execute. So these are permission bits that tell it what the program is allowed to do with that memory.
Is this going to have like how websites communicate, like one website to another website, or is it something more complex?
It's much lower level than that, but it's a similar concept.
Okay.
You know how Ben was talking about, just to restate in case people weren't there, Ben last week talked about the same origin policy, wasn't it? Same origin policy in browsers, where each website can only see the content of itself. It can't see what other websites are seeing. So like the sketchy website you open can't see your bank kind of thing. This is similar, but instead of websites, it's processes running on your computer. It's like Firefox can't see this presentation I'm presenting right now because I'm doing it in LibreOffice. Does that make sense?
Yeah.
Okay. And then one really cool thing about virtual memory that really speeds things up is you can also map the same physical memory to multiple processes. So they can share stuff. So for example, going back to our processes here, they're both probably using the standard C library, you know, printf, malloc, stuff like that. So it makes sense for them to share that physical memory. So like if the libc was here, libc would be mapped into both of their page tables. That way we don't have a copy of the standard library for every process that's running. Does everybody know what I'm talking about when I'm talking about like the standard C library? Cool. Okay, that's virtual memory. Does that make sense to everyone? Cool. All right. Next major OS topic, kernel versus user space. So the OS kernel is the core of your operating system. It interacts with hardware and manages memory and other like system resources. So your kernel is the one that orchestrates all of the page tables and memory sharing and all that fun stuff. And then you also have this concept known as kernel space. Kernel space is a higher privilege mode your CPU runs in when executing kernel code. So there's like a physical bit in your CPU that says, are we in kernel mode or not? And when you're in kernel mode, you can do additional stuff. Like manipulating page tables. Let's see. Oh yeah, and some examples of when the kernel might execute. It might execute for system calls. So like if you're reading or writing to hardware, for example, like if you're reading or writing to disk, your kernel deals with that. If you are switching between processes, your kernel deals with that. And if your process just segfaulted or tried to divide by 0 or did something that the hardware didn't like, your kernel also responds to that. So basically what you need to know about this, oh, there's another slide. Here we go. So your kernel code has its own section of memory. Okay. Which has its own, it's not drawn in here, but it has its own like stack heap and stuff for the kernel, right? And oftentimes your program switches back and forth between running kernel code and running user code. Now, because it does it so often, it's really important that it's able to switch back and forth quickly. And we could, because again, the kernel has access to different memory than your process. We could switch out our page tables every time we switch between kernel code and user code. But that's really time consuming and expensive and you don't do that. So instead, what operating system designers said is, hey, let's always have it mapped up here. But it's really important that user space processes can't access kernel space. But let's just not set any of the permission bits. So it's always mapped here, but the permission bits say you're not allowed to read from it, you're not allowed to write to it, you're not allowed to execute from it. But it's still there. That shouldn't matter, but for this attack, it really does. And again, to restate it, it is very, very, very important that user space programs can't read kernel space memory. If user space programs can read this memory, everything breaks. You can read all of your, any keys or encryption keys that are sitting in memory, any passwords that are sitting in kernel memory, bunch of stuff up here that you don't want your user space programs to read. Everybody good on that? Everybody good on kernel versus user space roughly? All it really is a higher privilege mode your CPU runs in when it's running kernel code, because kernel code needs to access a bunch of low-level hardware stuff. Awesome. And oh yeah, I have to highlight the meme down here. Foreshadowing nothing, the fact that user space programs can't access kernel space. All right, now we're going to move on from from operating systems to processors. So, modern processors use a technique called pipelining. If you've taken 315 or 333, you probably studied this a fair bit. Use pipelining to execute multiple instructions at the same time. However, sometimes, when they're doing multiple instructions at the same time, you immediately need the result of the previous instruction for the next instruction. So, to talk about that, let's say we have our basic C pseudocode example up here. We are calculating myvar equals 2 plus 2. We're assuming this is done at runtime, not compile time, don't worry about it. So your CPU calculates myvar is 2 plus 2. But while it's doing that, it's also checking this if statement. But it doesn't know what myvar is yet, because it's still calculating it. So what we used to do is we used to just sit around and say, okay, I'll just wait for myvar to be done calculating, doing nothing, wasting CPU cycles, pointless. So at some point, somebody, don't know who, said, why don't we just take a guess? Doesn't matter if we're wrong, we have no we're not doing anything anyway. Let's take a guess. Let's say myvar is 4, and assume it's 4. And so it starts executing this code. Now if myvar was 4, then the CPU, cool, we've done all this extra work that we wouldn't have otherwise done, we've gotten a head start. If myvar isn't 4, then, there's a name for this, but I can't remember what it is. But basically what it boils down to is we're going to throw out the result, throw out everything we did, and start again on this section of code. This is called branch prediction. So the process of figuring out which branch we're going to take, if we're going to do the if or the else, that's branch prediction. Process of actually running the code before we know if that's the correct code to run, that's called speculative execution. Speculative execution is going to be very important for this particular vulnerability. So, does that make sense to everyone? We're basically just taking some time where we weren't running anything and just taking a guess at what we should be running, trying it out. If we're wrong, we throw the result away. If we're right, we get to keep the result. Cool. Now take that and make it about 10 times more complicated. This is a diagram from the original Meltdown paper of, I think this is a Skylake Intel CPU. A lot more complicated than what I was talking about. But really all we need to know is it fetches instructions up here, it breaks them up into what we call micro-ops. So, I'm not going to get too into the weeds on this, but basically x86 takes its instructions and breaks them up into smaller instructions, takes these micro-ops, and then feeds it through all this stuff, and eventually they get down to the actual units of the CPU that do the math and do the work. So there's one unit down here for storing data. There's multiple ALUs which actually do the math on the CPU. Yeah, we don't really care about that. But what we do care about is that when we're speculatively executing, we can't just commit the results to registers or memory because we don't know if they're right yet. So they get committed, they get stored in these buffers down here, right? And then once we figure out if we were correct in our branch prediction, then these registers get committed to registers and memory. So all you really need to get out of this is that we are running code that we don't know if we're supposed to be running yet. And that shouldn't matter because we don't commit the results until we know we were supposed to run it. But there's some asterisks in there that make that a bit more complicated. All right, on to caching. This is the last topic we're going to go over before we actually get to talk about Meltdown itself. So, basically all you need to know is CPU memory, system memory, slow, dog shit, don't like it. We need something faster. Modern CPUs are like 10, 20, 50, I don't know, a lot faster than modern system memory. So we introduce a cache between the CPU and the memory. Now the cache exists, hang on, let me finish drawing. Okay, so the cache exists between CPU and memory. So when we fetch some data from memory, it goes through the cache to the CPU, and it gets stored in the cache. And then the next time we need it, the cache can say, wait, you don't need to go out to system memory. I have that right here. Now the cache is a lot smaller than system memory, so it can't cache everything, but it caches our most frequently used data. So that most of the stuff we're using, we just get from the cache, and it gives us a huge system speed up. And that's because the cache is actually like on the CPU die. So it's like, I mean, you can kind of see this diagram up here, how fast things are. Main memory, 100 cycles, caches, 10 cycles, and then one cycle is just like a CPU cycle. Anyway, there's also different layers of cache. So we have L3 down here, big and slow, L2, smaller, faster, L1, very small, very fast. And also L1 and L2 are per core. Okay, anyway. Yeah, so that's what caching is. Does that make sense to everyone? Cool, all right, now we're gonna bring it all together. This one slide is probably gonna take me like 10 minutes. Again, if you have a question or something that doesn't make sense, please just interrupt me, because this stuff's kind of complicated. So, thanks for Dr. Beard. He wrote this code and I modified it slightly. You should definitely take CPE 426, which is where I learned all this stuff, hardware security. Anyway, on to what's actually going on. So, to start off, we write our kernel address into a pointer. We're just assuming this exists in kernel memory. We can't or shouldn't be able to access the data at this address, but we're going to anyway. So we initialize this array, or we don't even initialize it, we just declare it. Probe array, it is of size 256 times 4096. I don't know how big that's about 1 megabyte. We're going to get to why it's that big in a second. And then we are going to try to load an address from kernel memory. So we have this kernel address, we're going to dereference it. Should it be able to do that? Right here, right now. The CPU should say, excuse me, you can't do that, and raise a page fault. Which it kind of does, but because of speculative execution, it doesn't realize it's supposed to raise a page fault though. So from here out, it's speculatively executing. So it's still going to run this stuff, but it's not going to commit the results to registers or memory. So it doesn't matter, right? Said some Intel engineer somewhere. So what we're going to do, again, this is all speculatively executing. We have the kernel memory value. This is the value we're not allowed to have. We're going to multiply it by 4096. That's all this line's doing. And then we are going to index into our probe array with this final kernel memory. Again, none of this data actually gets committed anywhere. What does happen, actually continuing down here, at some point we are going to get a page fault because we can't just continue speculatively executing forever. At some point the CPU realizes, like, hang on a second, you're not allowed to do that actually. So at some point it figures out that we weren't supposed to access that memory. It says, okay, I'm going to throw out all that stuff you did while you were accessing that memory. And you can just catch the page fault. If you didn't know, you can write a bit of code that the kernel runs whenever your process receives a seg fault, so you can recover from the seg fault. In our case, we're just going to say like, we intentionally raised a seg fault, so we're just going to keep executing, and we're going to go through each of the probe arrays. So what's important to understand here is that none of the results got committed. You know what did get committed though? The cache. So even though it's speculatively executing, it still loaded the result. It still loaded this value of the array into the cache. So currently, we have our probe array, and I forgot to go over, sorry. We basically cleared the cache before we started. You can do that in x86. I don't know how to, so it's not here. You also can't do it, you have to do it in assembly. That's a thing you can do, but I'm not really going over it. But we did. All right, so we got our probe array. It's all of garbage data. The entire thing's full of garbage data. We don't care about any of what's in here. What we do care about, though, is that one of these pages got loaded into the cache. One of these is cache, the rest of them are not. That's what this did, because we loaded the value, so it was loaded into cache. And then what we're going to do is we are going to iterate through all of the probe array addresses, and we're going to see which one comes back fastest. Because we're going to go through, we're going to say, okay, starting here, this has to load from system memory, so it's slow. We're going to go here, has to load from system memory, slow. Eventually we're going to get to here, this one's cached. So it's going to be fast. All right? And if you remember, the address or the index of that is final kernel memory. I'm not going to write that down actually. It's final kernel memory, which is just the value we got out of the kernel memory times 4096. So we just divide by 4096, and we have this variable, which is the value in kernel memory that we weren't supposed to be able to access. So we've retrieved 1 byte from kernel memory, which is useless. But you can just keep doing this again and again and again and access the entirety of kernel memory. And through that, you can just dump the entirety of kernel memory. And as a reminder, like that's where a bunch of encryption keys and passwords and SSH keys and stuff are that you don't want processes to be able to access. You can also potentially access other processes. I'm not exactly sure how that works. I don't know why you have other processes mapped into your page table, but I think you can do. Any questions on this? Or any just like vague, like any spots where you're just kind of vague or kind of don't know what's going on? This is really weird, really complicated. When I learned it in class, I basically just stared at it for 15 minutes after he explained it, until we all kind of got it. Raise your hand if this actually makes sense to you. Kinda? Kinda, okay. Is there any, if you had to pick a line of code that made the least sense to you, which one would you pick? Or a concept? Or you want me to just go over the whole thing again? I could do a better job of explaining it the second time probably.
The one with the comment raises the page fault.
Do you want me to go over like just the fact that it raises a page fault, or like the entire line?
The line.
Okay, so this is the line where we're doing, basically, we're taking our kernel address, so this is just a random number, don't worry about it. This is an address that we know exists in our kernel memory, which, as a reminder, we are not supposed to be able to access, but it is mapped there. So you don't have the permissions to access it, but it's there. So we're going to dereference it. So we're going to get the value out of that pointer. That's illegal. We're not allowed to do that. But the CPU doesn't realize we're not allowed to do that and starts speculatively executing past this point. I feel like that was a worse explanation than the first time. But did that make more sense or less sense?
Mm-hmm. I realized that it starts speculating after that line, not before that line.
Yeah, exactly. So it starts, this is where, in an ideal world, the processor would stop. It would not execute these lines. It would just stop here and say, no, you're not allowed to do that. It would raise a page fault, cut everything off. But again, because processors speculate past, in this case, a permissions check, they just keep executing speculatively and commit those results to cache. Any other like questions, foggy spots, thoughts? All right, cool. This is gonna be a short talk then. I kind of anticipated spending a bunch of time on this. All right, and then what does this mean? So, as a reminder, this is a hardware vulnerability. This is like one of this Spectre and Meltdown, which again we're not going over Spectre because it's too complicated. Between this and Spectre were like some of the first identified hardware vulnerabilities in like modern Intel CPUs, which means you can't patch them with software updates. Like it's in the CPU, you can't. There's no take-two backsies unless you want to just recall everything with an Intel CPU and since 1995, and send out new ones. So Intel didn't do that. Now there is a software patch. Windows, macOS, and Linux have the patch. Basically, in the case of Linux, we can look at the source code and see what the patch is, and the patches basically stop mapping kernel space into user programs. So, like I said earlier, now instead of just setting the read, write, and execute permissions, we have to actually go through the process of adding the kernel space to the page table. So going back to the diagram, like basically this isn't here anymore at all. It's just gone. But that means we have to put it back there every time we want to run kernel code, which is kind of expensive. Hello, can we move along, please? Originally it was forecast this would have like a 5 to 30% slowdown, which is like kind of annoying when your CPU just runs 30% slower because an engineer at Intel made a mistake. This never really materialized though for most workloads. Obviously it's worse if you're switching between user and kernel space a lot because that's where the penalty is. But for most use cases it was like kind of fine. Intel patched the vulnerability in their CPUs after that generation. And so yeah, oh yeah, and they also rolled out, going back again real quick, it's kind of crazy how complex modern processors are. Apparently, wait, I went way too far. They have like their own almost operating system running in hardware on the CPU to manage the breakdown of, okay, this is the picture I wanted. So like this process of like breaking up this instruction into multiple micro operations and then like scheduling them all throughout this thing, that process is like its own like little OS inside the CPU. It's like kind of crazy. And as of such, you can actually reprogram that OS. It's called microcode. And so Intel was able to patch some of their CPUs through microcode updates. Sometimes, I think they tried to do like the few years leading up to 2018 when the bug was discovered. They patched those. This also only really affected Intel CPUs basically. It affected like a couple other CPUs from ARM, I think. But AMD was not affected, which was kind of funny because they run the same architecture that Intel basically invented. I didn't have a lot of memes in this presentation because there aren't that many Meltdown memes, so I had to end on a Meltdown meme. I actually didn't know this until I saw this meme, but basically Intel argued that like this isn't a bug, this is like intended behavior of the CPU, which like it super isn't. You should not speculatively, in terms of patches, like I'm not sure what they actually ended up changing, but you either A, shouldn't speculatively execute past permissions checks, like that's the equivalent of like a bouncer at a bar just being like, you can go in, but if I find out you're under 21, I'm kicking you right back out. Like, you shouldn't do that. Or like not committing speculative results to cache. Those are both bad things. So yeah, okay, that's my talk on Meltdown. I hope that didn't melt everyone's brains too much. I know it melted mine when I learned about it. But yeah, anybody have any questions, concerns, comments?
Why are the AMD processors unaffected?
I don't know the exact reason. I'm not sure if anyone does, just because, again, like, it's one of those things that's like, it's proprietary information, but either they don't speculate past permissions checks, or they don't commit speculated results to cache, most likely. Ben, do you know? No? Okay, I'm just wondering. So yeah, don't know exactly, but it's probably one of those two, because those are not super great ideas.
What do you think they did to like patch it for future generations after 2018?
Don't exactly know. Again, I'm assuming it's one of those two. They're not like, I think in class we did say it was like not speculating past permissions checks, which has a performance penalty, because due to the way caching works, which I'm not, if you want to Google like page table translation look-aside buffer, you can understand more about this. But basically there's like a penalty to looking up these things in the page table, and that takes some time. So now you just have to wait for the page table to do its full lookup and check the permissions before you start doing anything else. Yeah. Any other questions? Cool. Oh yeah, and then one more thing. This also kicked off like a bunch of researchers doing a bunch of research into hardware vulnerabilities, and it was kind of funny because they just kept, like Intel kept adding other patches, particularly for Spectre, because Spectre was much harder to patch than Meltdown. They developed this technology called Intel SGX, which is like Secure Guard something. And then people found like vulnerabilities in that, and then Intel kept trying to make new stuff, make new, better stuff that wasn't vulnerable, and researchers kept finding vulnerabilities in Intel CPUs. It's kind of funny. AMD's had like a couple since then, but really Intel's had to bear the brunt of these vulnerabilities. All right, cool. That's all I had. Hope everyone enjoyed the talk, and have a good strike week.